Hi everyone. Just answering your feedback questions from today's lecture on valence bond theory. This one, why is it that sp2 orbitals usually form pi bonds? What is the trend for that? So I actually want to reread that and sort of tease out the wording here, because the wording itself is has a misconception in it. And the question is, why is it that sp2 orbitals form pi bonds? It is very, so there is some truth to this. Normally, if something is forming, if carbon is forming pi bonds, there's a good chance that it's sp2 hybridized, or rather we say it's in an sp2 hybridization state. But it's not the sp2 orbitals that are making the pi bonds. The pi bond is formed by two p orbitals, one that overlaps here, another one that overlaps at the bottom. The two p orbitals are pointing up side by side; they overlap, and that's what makes a pi bond. When an atom uses sp2 hybrid orbitals, it has usually one p orbital left over to make pi bonds. So anyway, the question was, why is it sp2 orbitals usually form pi bonds? They actually don't. They usually make sigma bonds. It's the unhybridized p orbitals which are left over to make the pi bond. So let me illustrate that with an example here. So this is 4-maldehyde, so I have carbon doubly bound to an oxygen atom and singly bound to two hydrogen atoms. If I were to apply VSEPR theory to this, the geometry for the carbon, its VSEPR formula is AX, ooh, that's no good, is AX3. So I predict that it's going to be a trigonal planar geometry. And to make a trigonal planar geometry with 120-degree bond angles, the only way to make bonds at those angles is if I utilize sp2 hybrid orbitals. sp2 hybrid orbitals, they will point at 120 degrees from each other, as opposed to s and p orbitals, which are normally at 90 degrees to each other. So I have to use sp2 hybrid orbitals. So the idea is you take carbon's 2s and 2p orbitals, you hybridize one of the s orbitals and two of the p orbitals, and you create three sp2 hybrid orbitals. One of those p orbitals remains unhybridized, so it's left on its own left to its own devices. And so that is what gives you this basic structure here. So this is supposed to be the orbitals on that carbon atom. It again has these three sp2 hybrid orbitals, which are supposed to be at 120 degrees from each other. And it uses those sp2 hybrid orbitals to make sigma bonds. It makes one sigma bond with a hydrogen, and it makes another sigma bond with a hydrogen, and it makes one sigma bond with one of the two p orbitals in oxygen. Oxygen's electron configuration is 2s 2p4, so it has two unpaired electrons in p orbitals. It can use one of those to make a sigma bond with carbon's sp2 orbitals, and then the second bond, so normally a double bond is one sigma bond and a pi bond. That pi bond is then between the non-hybridized p orbital of the carbon and one of the p orbitals on the oxygen. So this is where the pi bond forms, sort of above and below. And I admit it's harder to see the overlap just because I've drawn these so far apart, and I drew them that way specifically so you could visualize it. It's easier to see where the orbitals are. If I make them really, really close and actually draw them overlapping, it becomes a big mess, and it's just harder to visualize. But that's the basic geometry. You can only form pi orbitals, really, with p and d orbitals. You can't form pi bonds with hybrid orbitals because they don't have the right geometry. A pi bond is one which has that above and below, that parallel style bonding. An sp2 orbital has one giant lobe and one small lobe, and it uses the large lobe to make sigma bonds. So I could have, that's essentially what I'm drawing here. I have an sp2 hybrid orbital. So this is the sp2 hybrid orbital, and then I could have, say, a 1s or a 2s or some other type of regular s orbital. They can point and directly overlap with each other and make a sigma bond. Pi bonds, again, have to have that parallel style bonding pattern above and below the internuclear axis. So this is what we call the pi bond. And yeah, there's 2 points of connection, but we consider it to be a solitary bond. I don't want to say single bond because that has another connotation. Anyway, so I hope that clarifies your question. It's not that sp2 orbitals form pi bonds. If an atom is sp2 hybridized, it will tend to form pi bonds because if it's sp2 hybridized, it normally has one p orbital that is left unhybridized, and then that p orbital can make a pi bond. And that so frequently a carbon that's sp2 hybridization state will be making pi bonds, but it's not making those pi bonds with the sp2 orbitals. It's making those pi bonds with its non-hybridized p orbitals. When do you know to promote electrons, and does it work with more than s and p orbitals? I almost hazard talking about promotion energy. How do you know when to promote something? You promote it if you need to. So when you're trying to form extra bonds, like previously, like with carbon, we started previously with this extra electron should have been down here. And in valence bond theory, this type of configuration would suggest you can only make 2 bonds with these half-filled electrons. So if you wanted to make more than that, if you wanted to make, say, 4 bonds, I would need to take this electron and put it up into the p orbital. And that is when we will say, okay, you pay a promotion energy. How do you know when to do that? Again, the answer is when you need to. So I always, maybe it's me being cynical, but I always imagine that a lot of questions are sort of coached from the perspective of like, when do we need to know? When as the student do I need to know? That seems complicated and abstract, and I don't. What am I supposed to do with that? Short answer is I will never ask you guys to determine when you need to pay a promotion energy. It's more that I would say, sort of filling out the details is why I mention it. Technically, yes, you pay a promotion energy to make these extra bonds. And that can be more important when you really go into the details of chemical bonding. But in terms of when you'll ever be able to, you'll need to know when to promote electrons. You won't, and certainly not for this final exam. I'm sorry. I'm kind of cynical, so I imagine other people as being kind of cynical. That when will you need to know how to do that? Again, you won't. It happens when you need to do it, quote unquote. If you need to get extra unpaired electrons, and the only way to do it is to take them out of lower energy orbitals, paired electrons in lower energy orbitals, and bring them up into higher energy orbitals. And that can happen, when does that happen? That can happen, like for instance in sulfur hexafluoride. Sulfur also normally only has, like oxygen, only has 2 unpaired electrons, but sulfur can make up to 6 bonds for sulfur hexafluoride. So the way you can rationalize that is if I take, well, there should be, sulfur would actually be not 2s and 2p. Sulfur would be 3s and 3p. So again, sulfur and oxygen, they're in the same column of the periodic table, so they've got the same valence electron configuration. But again, sulfur can make sulfur hexafluoride. So how is it able to make 6 bonds? Well, not only does it have its, I'm going to run out of space here, does it have its 3s and 3p orbitals, it also has 3d orbitals. So one thing you can do is you can pay a promotion energy and take one of the 3s orbitals, put it up into the 3d, take one of the 3p orbitals and put that one up into the 3ds, and then I have 1, 2, 3, 4, 5, 6 unpaired orbitals, half-filled orbitals with unpaired electrons, and then I can make 6 bonds. So that is when promotion energy is invoked. It's not so much that you will need to know how to do that. It's more of, well, it occurs whenever you need to do it. And I will never be asking questions in that style. It's normally there we make the leap from you just need to hybridize things, and the only way frequently you can make all those extra bonds and do all this hybridization is if you pay a promotion energy first. And I would just say it's nice to know sort of under the hood that that's what's going on. Anyway. So this last question, the mixing of different orbitals is what causes the different shapes of molecules, ignoring lone pair of electron effects. So I would say it's actually the other way around. Mixing orbitals doesn't cause the different shapes. We assert that a molecule has a particular shape. Vesper theory, VSEPR, is the theory we use, or at this level that we are using to predict the geometry or the shape of a molecule. Valence bond theory requires that if you want to make molecules with that shape, you need to use hybrid orbitals. So it's not that, okay, mixing of orbitals causes different shapes. It's that different shapes, different geometries require orbitals that have been mixed. Because valence bond theory, and again, that's an idea that valence bond theory needs to utilize in order to explain where you can get more complex shapes of. Valence bond theory conceptualizes a chemical bond as an overlap of orbitals. The atomic orbitals that an atom has have a particular geometry. So for instance, again, oxygen, its 2p orbitals are all at 90 degrees from each other. So if you wanted to make bonds with these orbitals, those bonds can only be at 90 degrees from each other. So again, I have one sigma bond that is in this direction, and then I have a pi bond that's sort of perpendicular to it at 90 degrees to it. So for instance, oxygen here is able to make these bonds without utilizing any hybridization schemes. Carbon, on the other hand, does. Carbon, in this example, has a trigonal planar geometry, and you can't get that geometry using just s and p orbitals. The only way you can get it is if you introduce the idea of hybrid orbitals, and then those hybrid orbitals are at 120 degrees from each other, and that's what allows you to make bonds at 120 degrees from each other. So again, I just want to re-emphasize, it is not so much that we say, okay, hybridization causes particular geometries, it's that the geometry requires a certain hybridization scheme. Right now, all you have to work with is Vesper theory for predicting geometries. Later on, you guys are going to learn slightly different ways to predict the geometry of a molecule. In organic chemistry, you're going to get angry at me and realize that I've told you only a handful of ways to conceptualize and predict shapes. And really, there are a multitude of factors and multitude of theories to predict the shape of a molecule. And you'll learn all of those. But we're sort of working with the bedrock here, the lowest hanging fruit. And at this level, Vesper theory tells you, again, you have a certain geometry. The molecule should have that geometry. It should have that shape. And if you want to describe its bonding from the perspective of valence bond theory, where you treat the bonds as an overlap of orbitals, the only way you can get those particular shapes is if you're using hybrid orbitals. So that's why the only reason we really introduce hybrid orbitals is A, to further describe the bonding, the overlap of orbitals in a molecule, and secondly, to make sure that the orbitals that we're utilizing make sense in the context of the actual prescribed geometry of the molecule. So how should you predict hybridization schemes? The way it should go is you draw the structure, you assert what the geometry should be. It's either going to be trigonal, bent, tetrahedral, trigonal, bipyramidal, what have you. And then based on that shape, you assert it should have a particular hybridization scheme, because that's the only thing that would make sense. Okay, so those are all the questions from lecture today. On Wednesday, we are going to continue talking about this. I'll probably end up drawing this picture again. My plan for Wednesday was to continue talking about pi bonds, p orbitals, and non-hybridized p orbitals making pi bonds, and any geometry requirements that makes. We're going to continue developing that. And then on Friday, I was thinking of maybe doing a little bit with molecular orbital theory, but that will be it. All right, so if you have any questions, please feel free to email them or stop by and see me during office hours. Yeah, I'll see everybody on Wednesday otherwise. Have a good day.